It was Nikolai Copernicus who realized that the planets move around the Sun. Some time later, Tycho Brahe made astonishingly precise measurements with the naked eye of the positions of the planets. Using these data, Johannes Kepler was able to find three laws that describe the motion of the planets in the skies. The first law of Kepler states that the planets move in elliptical orbits while the Sun is at one of its foci. Remember that an ellipse is a two-dimensional curve that has two foci. The combined distance from any point in the curve to both foci is constant.
Aspasius, I want you to imagine that this is the Earth, and that each of these flames represent the two extreme positions of the Sun in relation to it, in winter and in summer. What would happen if both these positions were the two centers of one and the same circle?
But it isn't possible, mistress.
Wait, what do we know about a circle? We know that the center of a circle is always the same distance from any point along its perimeter.
Exactly.
Yes, so what if I divide the center into two, but what I keep constant is the sum of their two distances to the perimeter? Oh, all right, look, I'll show you, watch. As I move this rod along the chord, as one segment increases, the other segment decreases, and vice versa. Therefore, the sum of the two is always going to be constant. Do you see that? Now, what if we apply this to the movement of the Earth? What figure will we obtain? An ellipse! With the Sun at one of its foci. Because what is a circle except a very special ellipse whose foci have drawn so close together that they appear to be one?
This scene from the movie Agora is a great description of it, but it is not historically accurate, as we don't have any data pointing that Hypatia made this discovery. Nevertheless, he was a fantastic mathematician and astronomer back in the 5th century. An ellipse is defined by its major semi-axis and minor semi-axis. When both semi-axes are equal, we have a circular trajectory. The circle is just a particular case of an ellipse. The closest point to a planet, from a planet to the Sun, is called the perihelion. The farthest distance of the planet to the Sun is called aphelion. There is a parameter called eccentricity that measures how stretched is the ellipse. In other words, how far from a circle it is. Eccentricity is 0 for a circle. Planets move in ellipses, but the great achievement of Newton was to use his universal law of gravity and his second law of dynamics to deduce that the allowed trajectories of astronomical objects around the Sun are all conics. A conic is a curved result of a section of a cone. Hypatia was very good at conics. The 4 different conic trajectories are circle, ellipse, parabola, and hyperbola. The first 2 are closed curves. This implies a bound trajectory. The object has a negative total energy and is trapped. The other 2 are open curves. This implies an unbound trajectory. The object has a 0 or positive total energy and is not trapped. Planets, satellites, and asteroids have closed trajectories, ellipses or circles. Comets can have any trajectory. If it is a closed trajectory like the one of Comet Halley, then it visits the inner part of the solar system regularly. Some comets have open trajectories and they only visit the inner part of the solar system once, and they leave. Objects from out of the solar system have visited us also, this in open trajectories. The problem with comets is that they inhabit Kuiper belt or Oort cloud. These regions are the outermost part of the solar system, and a small perturbation can change the position and send them to the innermost part of the solar system where the planets live. Because comets are relatively small, dark, and do not glow, they are very difficult to detect, unless they are near the Sun. And there are a lot of them out there. If one of these objects is coming towards the Earth, we might not detect it until it is probably too close. But the probability that a large comet impacts the Earth is smaller the larger the comet is. Small but not zero. May science be with you.